I gotta do it tonight. I literally had so much to do. I've been dead. Dude, I have a lab. That's what I've been working on. Look at that. All the math. So like when I just get there, I just gotta build it and test it. So. Yo, bro. Oh yeah, no, I love that. I heard that. Let you go. He will never take this down, so you gotta take it down for him. Okay. It's not hard. Yeah, that's the issue with that kind of bread. That's your homemade bread. I ate it. I have. Next time you go. That's where I miss all my points. I
Okay, well, I'm gonna work until 7. That's it. Me and Bernie did it.
Oh, yeah. 7.
What'd you do, man? Dude, C has a triangle.
B was weird.
What I'm going to do is just stand and let this listen to quizzes. The average is 5.5. I'm just going to let them grab yours and pass it on. Now I can put people. I can put the solutions for both quizzes on just on OneNote if you want, or I can do them too. They're based on the homework entirely. How many actually realize these are homework problems? They're entirely homework problems. So if you do the homework and stay with it, then you'll see that the only thing that may change was a constants value instead of 1 or 2 or something like that. But they're homework problems, and that's all they know. That's all I ever do for quizzes. They're based on homework entirely. All right, today we're going to be talking about Laplace transforms. And I know you've had them. Really, I'm going to tell you a couple things about Laplace transforms that I consider most important. All the markers are down. One other thing I want to mention too, I don't know what the state is right now, but I understand we're getting some very bad weather between 3 and 5 today. Forgive me. It's probably AU alert. Sorry. Anyway, this is what I want to tell you. I don't know how bad it's going to be, but I got some kind of information that it might be severe, and it's supposed to get here between 3 and 5. If you're traveling, try to do so before then if possible. Now, about Laplace transforms. Did anybody get, is there any kind of a tornado warning or anything like that coming out?
Severe weather.
Alert?
Severe wind warning until like 10.
Well, wind is one thing, tornado's another. Hopefully no tornado. Before I start, does anybody have any questions about the homework or anything? I can put the quick, yeah.
3.7C.
Is this you using properties to do it?
Yeah.
Let me get back to you on this one, all right?
Okay.
Just give me a second. I want to show you something. This is the way I think it's my contention. The single best way to do Laplace transforms is start with the actual Laplace transforms pairs that you must know. You got to know these by heart. and then add to it the properties that you need to know so you can get anything you want. All right? I won't prove everything, but I'll try to get the ones that are most important. We're going to do the Laplace transform pairs. You must know this for sure. You've got to know the fundamental definition of the Laplace transform. S f of s or x of s is the integral from 0 to infinity of f of t times e to the minus st dt. That's the fundamental definition of Laplace transform. It's called a single-sided Laplace transform. We do not start the integral from minus infinity. That is called a double-sided Laplace transform, and that's something that is used, but not for most of the things. We're electrical engineers. We have our own clock. We can start the time at 0. Follow me on this class? This is an applied, this is a very applied course. So if this is the case, and S itself is some real value called sigma plus j omega. J omega is just like the frequency that you're used to thinking about when you had circuits. It could be 377 hertz, something like that. But it's got a real and an imaginary component, and we'll get to why that's important with what's called convergence in the S-plane later. But this is the fundamental definition. So now we get the functional forms you have to know. The first one, of course, is delta t. I put this there last time. If you look at delta t, what this means is if this is f of t, this will be f of s. Or I should say, let me do it over here so I can populate it. I can say if this is f of t, then in this column we'll put f of s. We're just going to populate a transform pair field. So if you have delta of t here, just by popping in delta t into that definition, when you have delta t, you look for where it turns on, where it goes to the infinite value, which is at t equal, just say it,
0.
at 0. So it becomes infinite at 0, and we know the area under the curve is 0, and what it does is sift the value of anything next to it at that time. Well, e to the minus 0 is 1, and therefore this transform is 1. Understand? Very simple. I don't need to write these up. These are pretty obvious, right? Next one that you do, typically do, is going to be a time, this is a property, but I like doing it, e to the t minus a. I put it right here because it's so useful. Now, if you take this as f of t and stick it here, where does it turn on at t equal a? Therefore, it simply extracts the value of e to the minus sa. You understand, class? That's it. This becomes e to the minus sa. And a can be 2, 5, 100. Doesn't matter what a is. It can be anything. And it can be imaginary too. So it could be like J35. So it doesn't matter. The next one that is typically done is e to the minus at. Try to draw that a little better. E to the minus at u of t. Now that's an exponential decay, correct, class? I'll do this one just so you get, because you will have to use that property to actually get the values at some point. This one's a pretty easy one. If I look at this, if I look at the transform of that, the f of s would be equal to the integral from 0 to infinity of e to the minus at times e to the minus st dt. To do this integral, you see how you have e to the minus at, e to the minus st. You can add those two exponentials together. I mean, this exponents. Can't you, class? So I can say that this, give me one. Yes, sir.
So anything that you're integrating from 0 to infinity, you can remove any u of t terms?
Well, that's effectively what I've done there. I mean, if you're going to go from 0 to infinity, u of t is always 1. I can't go below there, so I just get rid of it. But the only thing this does for you is say this only exists with non-zero values for t greater than 0. That's it. Well, this is going to be simply the integral from 0 to infinity of e to the minus the quantity a plus s t dt. And it's pretty obvious that here, this is going to be equal to minus 1 over s plus a evaluated from 0 to infinity. And this is going to be the value, times e to the minus quantity a plus st. When it's infinity, this term is 0. When it's 0, this term is 1. And it effectively, what's going to happen is, since there's a minus sign there, this just becomes 1 over s plus a. So this is 1 over s plus a. These are ones you have to know. How many remember these from before? Bet you most of you do. Most of you probably do. Next one is u of t. Now, I want you to just look up here for a second. What would the value of a have to be to make this function just u of t? Anyone? 0. And if it's 0, which is legitimate, there are no conditions on a, the transform would be 1 over s. Does everybody see that, class? Got one or two others to show you. How many see this right here? And far back, can you guys see it? My gosh. Hey, are you guys able to see the link on this class or not? How many have looked at it? I think it works. I think it works. Are you doing it yourself? You don't need to. He's got it right here. All right, I mean, I don't mind. Now, the next one I want to do, and I want to tell you, this is kind of an important one that people don't always catch on to. Suppose I have this functional form. I'm going to say my f of t or f of x is this. Here's t, and it's going to be 1 out to some point, and call it a, and then 0 after that, and this is t. So that's the function f of t, right? And I want the Laplace transform of that. Now, how many see that you can construct that out of two u of t functions? Show of hands. All right? Which means, and I didn't do the shift on this one, but I can say that this f of t here is actually u of t minus u of t minus a. Everybody with me? You have to be sure you understand what I'm doing and why I'm doing it. Now, I didn't actually show you this next part, but I'm going to just say this. I want to put it over here. This is the first property. I don't know if I need to prove this. But if I have x of t or f of t go to x of s, this is assuming we know this relationship. Follow me? Then when I have x of t minus anything, and I'll use a, it simply creates an e to the minus as times x of s. That's the only thing that happens. I'll prove that in 1 second. The reason I'm doing that is I can see that this is just a function with a delay. And I already know what u of t goes to in terms of its transform. Follow me, class? So we'll do this property real quick. This is the first property that's useful, that you can see where it's useful now. If I take a look at this, so I'm just going to go ahead and say, if I want the Fourier or Laplace transform of that, I would take the integral of x of t minus a times e to the minus st dt, technically from 0 to infinity. You all agree with me? It's a fundamental definition. What I'm looking to do is create something that looks like a Laplace transform there, and say that's x of s, and then whatever's left over will be the coefficient, or will be the thing I multiply by. Now, if I look at this, to do this integral, I create a new variable. U is equal to t minus a, and then du is dt. Now, you don't have to be, this doesn't have to be this form, but you have to know what's going on. Now, if I take a look at this, then this becomes the integral of x, right, of u, right? Then it's e to the minus, not t, but what? U plus a, correct? Because t would be replaced by u plus a. Can you all see that back there? So this becomes minus u plus a times t, and then times d, or I'm sorry, times u. T becomes u plus a times s, pardon me. Then it's times du. And now u, here's the thing, if t goes from 0 to infinity, u, well, let me see, bless you. And this is equal to minus a, and this is going to be to infinity of x of u times e to the minus us times e to the minus as du. I just put it down here, and I put the minus a here, but I'm going to make an argument. That's x of u. That was x of t. Now it's x of u. Are you with me? It's t minus a. Now listen to me. Because we make a conditional statement that x of t is only non-zero, these are only when these transforms are valid, for t greater than or equal to 0, we can actually make this lower limit 0. Are you with me, class? Because we've defined this transform only valid for things where t, x of t, the function, has values of non-zero for t greater than or equal to 0. Follow me on this? Now, when you look at this just for a second, the integral is with respect to u. That has a u in it, this has a u in it. I can take this e to the minus as out in front, and that's the transform. Look carefully right here. Isn't that really the definition of the Fourier transform, only instead of t I have u? You all see that? And you realize you integrate out the dummy variable t, call it a dummy variable. Are you with me, class? So in fact, this is the Laplace transform of x of u. And in fact, if you do a simple delay operator, the only thing you do is take whatever it's delayed by, and you take e to the minus that value as, and that in fact is the coefficient you multiply the original transform by. Understand, class? How many remember that one from before? I took a little more time. Yeah, go ahead, Fritz. A little more time here, but it's important to see this. All right. Now, this is in the book. So that's the first property. These are all properties over here that are useful. And by that, now I come over here and I can say that if I have this functional form, f of t is u of t minus a, what does it go to? Now just take a look. Well, what does u of t go to? Look down there. Class? 1 over s, right? Right? And then it's minus, what does u of t minus a go to? Well, that's going to be 1 over s, isn't it? Right? Times e to the minus as, right? So it's going to be minus 1 over s e to the minus as. How many see this right here? People, do y'all see it? Who doesn't see it? The only thing I'm trying to do is show you that I'm using a property now to get that. I've showed you the delay property. If I know u of t goes to 1 over s, then u of t minus a goes to 1 over s, the original transform, times e to the minus as. That was my point. Does everybody see that? Give me a show of hands if you do. It should be very obvious to you. Now, that means I can also take this and write it as 1 over s times the quantity 1 minus e to the minus as. That's an important one to remember. And the reason is, this is like a shifted pulse function, isn't it, class? This is perfect to use as a building block for a lot of things. Remember when you had those drawings where you had the wacky things that go up and down and you had to build them out of known functions? This is a good one to know because you know the transform of it easily. Follow me, everybody? All right, we'll keep going on this. So that's one. Now, the next thing I'm going to talk about, these are about the basics. I've got to do 2 more. Actually, maybe a little more than 2 more, but I want to do 2 that are kind of important. You have this written down? I'm going to erase this right now. Let's give myself the center board. So the next thing I'm going to talk about is this. And this is something that I'm going to bring about, something called Euler's identity. In electrical and computer engineering, you must know these by like the back of your hand. The first identity is e to the minus, really, I'm just going to put it e to the j theta is equal to cosine of theta plus j sine of theta. Theta can be anything, but it is angular usually. It's usually an angular measurement. What this really entails, e to the j theta, if you remember from circuits, what normally happened is you had a real axis here in the complex plane, and you had an imaginary axis here. And then you had e to the j something, which is just a vector, starts at the origin, goes out here, and it has a length of 1, right? And the angle theta was here. Everybody follow me? Now the vertical axis is j, the horizontal axis is real. So if you looked at this, well, what would the projection of that be on the real axis? Just look. it would be 1 times cosine of theta. Right there, right? What about the projection on the vertical axis? 1 times the sine of theta. Do you all see it? As theta increases, this revolves this way. Keep that in mind. E to the j theta is something that is a vector of length 1 that is oriented at the angle theta. And if this was a minus theta, for instance, I'm showing you this is e to the j theta here. If it was e to the minus j theta, it would be identical, symmetric, except now the angle would be here. It would be measured in the clockwise direction from the horizontal. How many remember that? When you had circuits with Dave Irwin or whoever you had, they would go through this. This is very important to know. So this is one of the first identities with Euler. The second is this. If I wanted to write what cosine was, remember cosine is just this length from here to here, in terms of e to the j theta, well, I could take e to the j theta divided by 2, that would be half the length, and then add to it e to the j, or minus j theta by 2, which would be this, and I would get the cosine. I'm going to write it down. So cosine of theta would be simply e to the j theta plus e to the minus j theta over 2. Do you all see that, class? It's adding 2 what? 2 vectors of length 1, right? But it's adding them at where you have e to the j theta, e to the minus j theta, right? When you add those 2, you get rid of the imaginary component, you're only left with the real, right? But that's 2 times the length that you want, so you divide by 2. How many see this? Also, you have to know this one. That's the main one. This is the second. The third one is going to be the sine of theta. Now the sine of theta is e to the j theta minus e to the minus j theta divided by 2. You can almost see what's going on here. If I have e to the j theta, I have this, length 1, right? Then if I subtract this vector from it, that's e to the minus j theta, now I get this, don't I? How many see that? Sure. And that's twice the value you want, so you divide by 2. But it's imaginary, so you got to divide by j to get the sine. How many see this right here? People, please write this down and look at it. Convince yourself of it. They're so useful. How many have used Euler's before? Now, everybody sitting here should have had a lot of exposure to it in your mathematics courses. If in your electrical engineering courses, when you had circuits, you should have seen that over and over again. Various forms. But these are the 3 essential forms that you need to know. Now, why is that so important? And I'll show you. You realize that I can create a sine, a cosine, and for that matter, I can create a tangent, cotangent, sinc, cosec, and any trigonometric form of interest to me out of really the e to the j terms. Right? Here's cosine, right? Suppose I wanted to know what happens, what the transform would be if I had cosine of omega naught t u of t over here. All right? Well, I can rewrite this as what? I can rewrite that as e to the j omega naught t, right? Plus e to the minus j omega naught t. Divide that by 2 and multiply it by u of t. Do you all agree with me there? Give me a show of hands. Stay with me on this one, even if you know it. Just make sure there's some tricks I'm going to show you in a little bit. So if we've got that, and I want the transform, you all see really I have e to the j omega naught t divided by 2 times u of t plus e to the minus j omega naught t divided by 2 u of t here. Do you all agree with me there? All right, now what about this transform right here? Just e to the j omega naught t times u of t. Look over here. We have e to the minus at u of t, and it goes to 1 over s plus a, right? What is a in that case if I have j omega naught t? A would be minus, right? It would be minus j omega naught, correct? Not t, but minus j omega naught. So the first one, you got a 1/2, I'll leave out in front. So then I have 1 over s minus j omega naught. What about the second one? Now it's what? 1 over s plus, right? It's 1 over s plus j omega naught. You all agree with that, class? Show of hands, how many see this? This is stuff you have to be, it has to be automatic after a while. You can't spend a lot of time wondering, oh, you've got to just do it often enough so it's ingrained in you. All right, now I want to condense that down to something a little more reasonable. So what I do is get a common denominator. I multiply this times this, right? And then I take this and I put it over here, and this I put it over here. So when I do that, I get 1/2 times, my common denominator is going to be s squared, right? Then I have what? S times j omega naught minus s times j omega naught, so they cancel out. And then I'm left with the last term is what? Minus j omega naught times j omega naught, which is omega naught squared, right? Because j times j is -1 with a minus sign is plus. So it's plus omega naught squared. What happens upstairs? I have s plus j omega naught on this one, right? Then I have s minus j omega naught here, or I have 2s. And that's it. How many see the 2's cancel? So the bottom line on this one is that the simple cosine by itself, cosine of omega naught t times u of t, just goes to s over s squared plus omega naught squared. How many knew that? Now, I know there are a lot of you know that. You're just not acting like you're going to boast, but I do know that. All right, that's the cosine. This is what cosine goes to. And remember, I'll just put down cosine right here. I'll just put down right here cosine of omega naught t u of t. All right, let me get rid of this stuff. We've got to do this other one. We've got to do sine too. What is sine? The sine of omega naught t u of t go to, class? Now think about it. What am I going to do with that sign? Just so I can do it easily. Yes, sir.
Is that a negative?
No, that's an eraser mark. They're positive. It's s over s squared plus omega naught squared. Sorry about that. All right, now what about the next one? All right, the next one is this. What is the sign? How many remember? It's e to the plus j omega naught t, right? Go ahead. E to the minus j omega naught t divided by, people, 2j, not 2j. All right, by 2j. Please put down 2j. It's by 2j, or else you get it'll have an imaginary value, all right? Then I have this divided by 2j, and it's all times u of t. Agreed, everyone? Come on, guys. Are you with me on this? I know it's boring, but yeah.
What's the divided by j for?
Remember, if I just take e to the j, or e to the j theta, minus e to the minus j theta, I'm on the j axis, right? I got to get rid of that, so I divide by j. That's the reason. Follow me? So you got to divide by j. Do you remember this identity from before? I mean, you don't? I mean, do you remember Euler's identities? For sine, cosine, e to the j theta? No? Really? We used to get those in high school. I'm kind of surprised. All right. I mean, those were real important. All right, well, let's do this. What happens, now I'm going to say this. This really breaks down to e to the j omega naught t times u of t minus e to the minus j omega naught t u of t divided by 2j, right? Each are divided by 2j. And I want the transform of that. Can you take a look at that for a second? What does this one become? Well, if I just had e to the j omega t u of t, what would happen over here? Let me get rid of this. You said it, you're right. So, the first one, I'm going to just put the 1 over 2j here because that is effectively just a coefficient. Do you all agree with that, class? I can bring the one. So I take this first term, e to the j omega naught t u of t. That's going to be 1 over s minus j omega naught. Isn't it, class? Right? How many see this? Please make sure you keep up with this. If you, for whatever reason, are confused, you really got to dig down deep now, because this stuff is, I'm assuming you know, because you've had it before. What's the next one? Now it's minus 1 over, say it again,
S plus J.
just as before. Only there's a minus, not a plus, and there's a 2j out in front. Correct, class? Everybody with me? All right, now, go ahead and get a common denominator. So I'm going to leave 1 over 2j there. And the common denominator is going to be s squared plus omega naught squared, as before. How many agree to that? Just multiply the two bottom terms, right? So now I get this, s squared plus omega naught squared. And then I have to take this, and I'm going to do it up here for this one, s plus j omega naught. And then I have to subtract this, s minus j omega naught here, right? Y'all agree with me? What do you see happening? How many see the s goes away on top? And I'm left with what? 2 times j omega naught. Am I not, class? Right? I got j omega naught here, minus a minus j omega naught is plus j omega naught. So I have 2j omega naught divided by 2j or omega naught. And therefore, this one is simply going to be omega naught over s squared plus omega naught squared. It's important to know that this is simply the sine of omega naught t, u of t. If this seems boring, just hang with me. I have to go through this one time. Now, after that, after you do that, everything else you do, basically with understanding how to get a Laplace transform or something, is using transform properties. Understand, class? Remember what I just said. It's using transform properties. What I'm going to do also is erase this part of the board. I filled in one property already. That was the shift, the time shift. We're going to go through a bunch of them. And if you have your books, can you give me the page number these properties are on in your book? I'm not going to prove them all, but I'm going to prove some. And I'll tell you one thing, even before I start this, I'm going to give you the most important property, in my opinion, for electrical engineers to save you the biggest amount of work possible. I'll prove this if you want me to. I prefer not to do it here, it's a little long. But this is the singular best proof. Again, we're going to say if we have an x of t here, and we want x of s. It could be f of t, f of s, it doesn't matter. So if we have, this is the property that I love the best. If I have some 2 functions, x of t convolved with h of t. Now you've learned to really love convolution, just like I did. Convolution used to drive me nuts, especially when you get a professor to decide to, give you one of these brain teasers where he has 3 functions, all of them not easy to understand, he wants you to convolve them all, just because he's mean. Well, I hated convolution for a while. But I learned to, first I understand the benefit of understanding it and how computers can do it very quick in real time. But the second thing is Laplace transforms eliminate the need to do it in most cases. Now here's why. These 2 functions, if they're convolved in time, the only thing you have to do is take the 2 Laplace transforms and multiply in the frequency domain, which is a world easier. It's much easier. And then if we wanted to get the actual convolution of time domain, we do something, it's called partial fraction expansion. We get that. That comes a little later. All right, class? That's the single best property. I can prove that to you. The only reason I'm not going to, it's a little longer proof. It takes about a board and a half, I think. I can do it though. And the book does it, by the way, the book does it. So that's my favorite property, the one that saves you time and energy. Once I have this, I can take that and do partial fraction expansion. Give me 1 second. And then you can go ahead and extract the actual time domain form. Go ahead.
I just want to know what it is. I see the x of s, but I don't know what it says like by that.
This is h of t, and we go to h of s. It's just the symbol h. My handwriting's horrible. And call me out when you don't understand something. That's the single best thing you can do for yourself. Never think there's a dumb question that's related to the subject. You can ask about Auburn basketball, then it's a dumb question. I mean, I'll just tell you this as a side. Football around here is pretty big. Long ago, we had a guy named Cam Newton, and he was pretty good. And you talk about I had a couple of Bama fans in one of these classes I was teaching. You want to see some really angry people? Come after the Iron Bowl that they lost in Bama and watch what happens. when you allow any questions. How come Bama lost? And then it just spun out of control. You can imagine that, right? I mean, you're young. You know what I'm talking about. Maybe you don't know what I'm talking about. Next thing we're going to talk about is another property. Remember, so far I've been keeping it simple. Now, there's some of the properties that are really useful is scaling. If I know x of t goes to x of s, well, x of at will go to 1 over a times x of s over a. I'm going to prove that one. So if you're looking at this, if I have the integral of x of at, here we assume we know the transform of x of t. Follow me? So we assume we know that transform. Then if we take this and we multiply it by e to the minus st dt from 0 to infinity, remember our goal is to get that transform. That would be the Laplace transform of that function, correct? Everybody in the far back, guys, I hope you can see. I worry about that. Frankly, I'm astonished that you can, but I'll take your word for it. So for this, what am I going to do next? Remember, I'm trying to turn that into something that looks just like a Laplace transform with something else next to it. Probably make at a constant, or some variable, right? So I'll go ahead and make u equal to at. That means du is equal to a dt, correct? Nothing fancy. Then I'm going to divide by a over here. So I have dt. And now I come up here and I said this is actually equal to, well, I'll come right here and do it, going this way. I'll say this is the integral from 0 to infinity now of x of u times e to the minus s. T is actually u over a, right? And then it's times dt becomes du over a. Do you all agree with that, class? I'm just replacing things, right? When I do this, do you all see the a can come out in front, right here? Do you all give me that, class? Now, watch. Here, can't I actually say that this is really like s over a times u? Isn't that right? Now take a look at this again carefully. Remember, u is the dummy variable, just like t was. It's something that gets integrated out and is not part of the solution of this integration. Well, the coefficient of u is really just like the coefficient of t. It is the s here, which becomes the operator there, doesn't it, class? So in fact, what this is a transform at 1 over a times x of, and then it would be s over a. And that's what I have here. So this is scaling. Are you with me? I can do an example of that, but how many see this right here? You probably want to see an example of it. Why don't we do this? Do a simple example. So I knew the transform of this when I had u of t minus u of t minus a. I'm just going to call this function now x of t. Remember, I can label this as anything, right? I'm going to label my x of t as u of t minus a. And I know the transform of that is x of s. And in this case, my x of s will be 1 over s times 1 minus e to the minus as. Do you all agree with me there, class? That's from before. We proved that already, didn't we? How many see this? All right. Now what happens if I have, remember, this is my definition of x of t. What if I have x of 5t? What happens? I want the transform of it. What do? What happens in the front of it? It becomes what? 1 over a. What is a? Make sure you see that. 1 over 5 times what? The actual transform, the original one, only instead of s, we have s over 5. Correct, class? So now I have 1 minus e to the minus, and this is going to be a over 5s. And that will both increase or decrease the size and change the width as well, won't it, class? Are you with me? So it's going to modify, or you could say scale that transform. So please be aware of that. That's a simple application of scaling. Understand, everyone? You get this a lot. All right, let's do a few more. Couldn't hear you, what?
Is that 1 over 5 at the beginning or 1 over
Yeah, and because 5 right here is the coefficient that would be the A here.
Would you still have a 1 over S at the front?
I'm sorry about that, yes. Sorry, keep me on target here. That's a bad mistake, sorry. All right. I want to say one thing on page, what is it, 99 in my book, it shows a whole bunch of actual transform pairs. You do not need to memorize that. You can get most of these from simple properties. I'm giving you the properties that are most useful. I got another one I've got to give to you too. Now, another property that's real important is if I have e to the minus at times x of t, what does it become over here? That a can be an imaginary number. It can be j omega naught. Follow me? So we could actually build the transforms of x of t times cosine omega t, x of t times sine omega naught t, or x of t times tangent omega naught t, wherever you want, based on knowing this. Now, I'm gonna do that one over here. I wish I had more boards. You know, in physics, when they slide the boards up and down, it'd be ideal for this, so we could populate transform pair tables, even with some of the ones that aren't in the book, but I don't, so I'm gonna have to erase this. But I'm going to do this one. I take a look at it, and it's equal to e to the minus at times x of t. That's my function, the equivalent of the old x of t, and it's times e to the minus st dt from 0 infinity. That would be the transform I'm looking for. Do we agree with that? Now, it assumes we know x of s, so it assumes we know the integral of x of t e to the minus st times dt from 0 to infinity. When I take a look at this, this is just my take on it. Every time I see an exponential, I always try to group the coefficients of the exponentials together. And in this case, it would be the integral of x of t, right? In this case, times e to the minus the quantity s plus a times t dt. Isn't that right, class? Are you with me? Now, take a careful look at this just for a second. It still goes from 0 to infinity. When I'm doing that right there, the coefficient of t is the key. The only thing that coefficient of t does, this s here, is becomes what that's operating on. It becomes the value inside the parentheses of the transform. Does everybody see that, class? With me? So whatever the coefficient of t is over there, as long as I get rid of any other exponentials there, that's this coefficient of this is just a simple function of t. Now I look over here, I have x of t times this dt. Well, I know x of t e to the minus st dt is x of s, right? So this becomes what? X of s plus a, correct, class? S plus a. And this would be x of s plus a. Take a guess at what e to the at x of t becomes. Take a guess. Right. X of s minus a. Now based on that, let me just finish my thought. Remember how we started with cosines and sines? Right? I'm just going to write this down. I don't think he puts this in his book, but if he does, let me know if it's in the transcript. These are some you'd have to, I'm going to run out of time, you're not going to be able to do it. If I look at a cosine of omega naught t, u of t, and I multiply it by x of t, and I want the transform of that. This is one of the single most important transforms you're going to know in electrical engineering. This is called modulation. And it's what AM radio is based on. When you have a cosine waveform and you modify the amplitude by weighing it by x of t, and x of t could be a voice signal. Now it's called modulation. And what you're doing is, what we're doing really, without saying it, is we're showing you the mathematical theory for amplitude modulation on AM radio. So when I do this, this cosine can look like x of t times, and this is just e to the j omega naught t over 2 u of t, plus e to the minus j omega naught t over 2 u of t. And lo and behold, I have x of t times e to the at, where a now is j omega. You all see that? Divided by 2, of course. And now this becomes 1/2. And then you're going to get x right here of s plus omega naught, or j omega naught. I said j, it's omega naught. It's j omega naught. S plus j omega naught.
Should be minus j omega naught?
It's going to be right over here. S minus j omega naught. I changed the order. It doesn't matter what comes first. Usually I put the plus first, but that's it. And really what it's saying is it takes the original transform, it adds j omega naught to it. Right here, divides by 2. I mean, really I should say what this effectively does is take whatever x of t is, divides it in half, scales it, and then shifts it out to plus and minus j omega naught instead of 0. I don't have enough time to talk about more about that. You asked me, I'm sorry, about a minute over right now. You asked me a specific question about a problem. Which one was it?
It was 3.7.
Let me say this, if you want to be dismissed, you're dismissed, but please leave that running because I'm sorry, I'm just going to try to do this. Go ahead.
Look it up.
Just tell me what it is and we'll do it together if you want. But you can go if you need to go.
Determine the Laplace transform of the following function.
Go ahead.
10 times sine of 3t over t u of t.
10 times sine of 3t u of t, right?
Sine 3 and then under there's a t.
Hold it. 10 times sine of what?
3t over t.
3t close parentheses.
Over t. Times u of t?
Yes.
All right, this is something I didn't have a chance to cover. It should be in the properties. If you have x of t goes to x of s, then x of t by t goes to, and there should be a property on that. Do you see it? If it would be multiplied by t, there would be a derivative. Divided by t is an integration. Do you all see that property? Give me the number of that property, because I don't have time to do it.
Frequency integral.
Which property though? Which number?
10.
Number 10. How about if I do that next time? And I'm sorry.
Okay.
I didn't have time. Now, Friday is coming up. Unfortunately, we didn't get a Monday class in. What I'd like to do now is give you this Friday a quiz on basic Laplace transforms. Basically, the Laplace transforms, I've given you something like if you had e to the 5t or minus 5t times, say, sine of 5t, or cosine of 5t u of t, or maybe t times e to the minus at. So the properties, I'm going to give you the 5 or 6 properties you need to know, and the basic things that I showed you there, and then I'll give you a bunch of problems to do with the solution so you can work through them, all right? Simple Laplace transforms, nothing advanced. I'm not going to give you t squared times e to the minus at sine of 5t. What? Yeah, I can put them on one now. Those quiz, I think that's actually a homework problem.